2017.
So, hello everybody. We're going to talk about reversing hardware security modules. So, some things about me. My name is Fodis Lukos. I work at SSL.com, a CA focusing on SSL and code signing certificates. I hold a PhD in computer science, and my work focuses on PKI, CA security, but I also do some vulnerability research and some reverse engineering. The outline of the talk, we start with some boring stuff about what is an HSM, the security requirements, and then we'll move on to the more interesting stuff, the Utimaco HSM, our target, the firmware, the TMS 320 C64X DSP, adding support to Capstone, and finally finding a vulnerability. So what is an HSM? It's a special cryptographic module that implements cryptographic algorithms, methods, and protocols. You can securely store cryptographic keys, you can manage keys, generate, perform cryptographic operations like encrypt, decrypt, sign, verify, and most of them come in two forms, either a network device or a PCI card. There are also some USB HSMs, but they're not used at all. The biggest players are Gemalto, that bought SafeNet. SafeNet is famous for their Luna series of products. Sample value for an HSM, $30K US. Another big player is Thalys, who bought Encipher. Sample value for a USB HSM, $10,000. These are some of their products. I just could bring a PCI card with me, couldn't bring a network HSM. And our target, Utimaco. Utimaco is famous for the crypto server series of products, and they have a ready-to-deploy PKI solution using EJBCA. EJBCA is a very famous product for setting up a CA. Sample value for network HSM, 15,000 euros. So as you can see, it's a business with a lot of money. Where do you use HSMs? PKI, all certification authorities must use HSMs. It's a requirement by the certification authorities and browsers forum. DNSSEC, again, if you read the DNSSEC practice statement for the root zone KSK operator, you need to use an HSM. Electronic transactions. PCI DSS specifies that you must use HSMs for certain transactions. So if you're going to implement serious crypto, you need an HSM. So as HSMs are used in critical applications, as we said before, there are a lot of standards that have been proposed to evaluate the security. The major ones are FIPS 140-2 and the common criteria. FIPS 140-2, the full name is the Federal Information Processing Standard Publication 140-2, and it's the US stuff. The first version was made at 2001 by NIST and then updated at 2002. It's what everybody uses. And it supersedes FIPS 140-1 and will be superseded by -3. There's a very funny story behind FIPS 140-3. 3 different drafts have been written so far, but none has been signed by the Secretary of Commerce. It specifies 4 different security levels. The first level has some requirements about the algorithms that are implemented. Level 2 adds some physical security controls. Level 3 has more physical security controls. Level 4 is about HSMs that can be used in physically unprotected environments. There's a special program, the Cryptographic Module Validation Program, that there are 22 laboratories that are accredited to make this type of validation for HSMs. The common criteria is ISO standard, it's the EU stuff. It has the valuation assurance levels, similar to the FIPS 140-2 levels. There are also some other stuff like protection profiles, security targets. The standard EAL4 says that all HSMs are methodically designed, tested, reviewed, and the best security practices should be used during design and test. I'm not so sure about this. So let's see the Utimaco HSM. These are some models of the Utimaco HSM, the crypto server. These are not that important. So specifications. It's a FIPS 140-2 level 3 device. It also fulfills the common criteria EAL4 augmented. It can be used for, it is used by CAs. It has support for many algorithms. It comes in both PCI Express card and a network HSM. And depending on the license, you can get more transactions per second. Well, this license check is a simple check inside the firmware, and you can change it at any time. But you won't have a FIPS validated firmware. But the funny thing is that I can assure you no CA uses FIPS validated firmwares, because FIPS is too old, and RSA with 4K bit key is not valid FIPS mode. So no CA uses FIPS validated firmwares. The hardware, actually network HSMs are simply Linux boxes with a PCI Express HSM inside. The PCI Express HSMs, as you can see at this one too, they have a special physical protection layer. There's a battery inside. If you try to erase, if you try to breach this thing over here, the contents of the memory are erased. Even when the HSM is powered off, there are sensors that detect changes in temperature, in voltage. It is supposed to be tamper-proof. Inside the PCI Express HSM, we can find the TMS320 C64X DSP. This is the DSP that performs all cryptographic operations. There's a true random number generator and crypto-secure pseudo-random number generator. And we have this keyram. The keyram contains a special key called the device key. Actually, this is something like a password manager. Everything is encrypted using this device key, and the device key cannot be extracted, cannot be exported, imported. You have no access to this key. If you tamper with the HSM, this device key gets deleted, so you lose everything. There are also the master backup keys, which are, according to the specification, 256-bit AES keys or 128-bit triple dash keys. That's what the specification says, the manuals of the Utimaco HSM. Of course, triple dash does not support 128-bit keys. No idea why they wrote all this stuff. These master backup keys are used to encrypt backups of cryptographic keys. They work using an N out of M scheme, using Samir's secret sharing. And keys inside the HSM are always encrypted with the previous key, the device key. And when you want to export them, they're encrypted using these master backup keys. There are some tools that come together with the HSM. There's a command line tool to manage both the PCI Express card and the network HSM. There are command line tools for communicating over the PKCS11 API, special API, the CXI API, and there are Java versions of the above tools. And there's also a simulator. It runs its own firmware, and this will, as we will see later on, this will be very useful. There are some other stuff like users, permissions. We're not going to see a lot of this. They're not that important. There's a custom communications protocol. Network HSMs use exactly the same protocol. There's no public specification. We just know that it's encrypted and uses message authentication codes. And now we'll move on to the Utimaco firmware. The firmware is a single blob in a custom format. There are both FIPS and non-FIPS versions. So after reversing a lot of things, I figured out that CSATM, the tool that comes with the HSM, has an option to unpack these files. So first lesson learned, always read the funny manual. Yeah. And after unpacking this MPKG, you get a number of MTC files. These are, for example, the MTC files from the latest firmware for the SE series. These MTC files are individual firmware modules. Each of them is associated with a specific function. For example, you can see here, this is for administration, this is for implementing the AES encryption and decryption functions, ASN.1 encoding and decoding. Everything is in here. So let's use Bingwalk. And we get this. 4 copyright strings and 1 Unix path. Nobody uses a standard format. Okay, let's use hexdump. So if you use hexdump, you can see over here, there's something that seems like a magic string, MTC header maybe. There's also a description. And later on, you can see 2 strings, .text and .data, that seem to be names of sections. So maybe it's a modified standard format, and that's why Bingwalk couldn't find out what it is. Okay, let's reverse the administration tool and see if we can find any info inside. After some hours, we could find these strings. So these should be COF files, but why didn't Bingwalk recognize this? Someone thought it would be nice to add their own stuff inside the standard COF format. Okay, so now what? We first identify the length of the section header. We can find the difference between the names of the sections, and this should be the length of the section header. We then fit this record to the standard COF section header. The next step is to make exactly the same thing, but for the COF file header. And finally, we've got a COF file. So now what? Of course, use IDA. And IDA supports this architecture. We open the file, and we get this thing. Of course, this is not assembly code. And now we can insert multiple slides with facepalms and R2, some binutils stuff. Only Texas Instrument had a disassembler, but it is completely unusable, and I also found some bugs at their disassembler. Okay, so let's write our own disassembler. To write our own disassembler, we must first study the architecture of the DSP, then study the memory organization, study the ABI, find some potential frameworks you can use, and finally write the actual disassembler. The architecture is a very exotic architecture compared to x86, ARM, MIPS, anything I have seen at least. It's a very long instruction word DSP. It has 8 functional units. The functional units are something like mini CPUs inside the DSP. Each functional unit has its own assembly instructions. It can execute multiple instructions in parallel at different functional units. It has 2 data paths with separate register files and a cross path to transfer data between those 2 data paths. This is the block diagram. This is the first data path, and this is the second one. Instructions are fetched, and they're dispatched to the correct functional unit. The forward functional unit's teach data path is the .l functional unit, which is an ALU, the .s functional unit, the shifter, there's also a multiplier, another subtractor, and the register file with 32-bit registers. And as we said before, this is the cross path between the two data paths. 8 execution units can execute up to 8 commands in parallel. Of course, at any single time, only one command can use the cross path. How are these executed in parallel? The DSP fetches not a single instruction, but fetches 8 words in a single fetch packet. So this can be scheduled to be executed at different functional units. And you can execute instructions in parallel that belong to 2 different fetch packets. The registers. There are 64 general purpose registers. All functions operate on 8, 16, 32, or 40-bit data, not 64-bit. For 40-bit operations, one register from the even register file is used, and the corresponding register from the old file is used for the 8 bits. So if we use this register pair, 32 bits are read from A10 and 8 bits from A11. There are also instructions that operate on packed data, like SSC, for example. And the only instructions that operate on 64-bit are loads and stores that are performed in a single operation. Furthermore, 6 registers are also conditional registers. All instructions at this DSP take a conditional prefix, and those instructions are executed only when the corresponding register is either 0 or non-zero. There's also the register control file that has control registers like the program counter, interrupt clear register, interrupt set register, and a lot of stuff. These are some sample instructions. This is the instruction shift right. It will be executed at the .s1 functional unit, and it shifts right A1 by 10 and stores the result to A2. This is another instruction that's executed at the same functional unit, but it uses the cross path. This is the X over here, because it needs to transfer from register file B to register file A. These 2 instructions will be executed in parallel. These 2 bars over here mean that they will be executed at the same cycle, but at different functional units. And this is an if-then-else in a single that will be executed in a single cycle. If A0 is equal to 0, then this command will be executed. Otherwise, this command will be executed. And all this is executed in a single cycle. But not all instructions are executed at a single cycle. There are some multi-cycle instructions that read the source operands at one cycle and write the result at a different one. For example, branches. Branches read the jump target at cycle I and jump to this target at cycle I plus 5. In the meantime, this register may change its value, everything may happen. There's a table over here, not that important, specifies the write cycles. So, if you still wonder why no tools are available, it's pretty exotic architecture. I mean, it's pretty difficult to make tools for this thing. Let's see the memory organization. We have a 32-bit byte addressable address space. It can be used using 2 configurations, either on-chip memory or off-chip memory. If you use an on-chip memory, you have 2 separate spaces, the data space and the program space. If you use an off-chip memory, then these are unified via the external memory interface. Some calling conventions. No stack exists, at least as we know it from x86. To call a function, you need to calculate the return address, by adding the program counter to the relative offset of the return address using a special assembly instruction. Then you store this to a register B3, and you jump the target, and finally to return, you jump back to B3. If the displacement is larger than a 21-bit word, the linker must generate some trampolines to jump to the final location. This is an example of a jump. So we have the branch over here. The target is read at cycle 1, let's say. This is executed at cycle 2. This is executed at cycle 3. It stores this one over here is the return address, the relative offset. It adds this to the program counter. It stores it to B3. Then this instruction is executed. The following two instructions are executed in parallel. Finally, the fifth instruction is executed, and then the branch is taken. At the end, this is a return, and it returns over here. So this is how you call a function. There are 12 call is save registers, some special registers. As I said before, B3 keeps the return address. You can pass the first 10 arguments in registers. So we know the architecture, we know the memory layout, we know the API. Now what? We have some framework choices. You could use binutils or LLVM, but this is too much work. You can use R2, which is a potential choice, but I found it much more attractive to implement new architecture at Capstone. So, Capstone. Capstone is based on LLVM, and it's open source, written in pure C. It has bindings for many programming languages, but unfortunately, you can't find any documentation on adding a new architecture. So how do we start? Okay, let's first clone the project, see how other architectures are implemented, and try to implement our own. How do you implement an architecture? We must write a table.gen file. The table.gen file has a description of the architecture, and it helps generate the register, instruction, sub-target info files, the disassembler tables, the assembly writer, using a special LLVM tool. But there's a lot of stuff that we need to implement too. So let's first generate this file, and we'll see about the rest. The table.gen file format. It's a file containing targets, sub-targets, processors, the instruction set, registers, calling conventions. But in our case, we won't need the calling conventions. After all, we're just generating a disassembler. We won't do any compilation. We don't need the instruction selection pattern. LLVM needs this to convert from the IR to the final assembly. And we won't need the many flags. What we will need is the description of the registers and description of the instructions with the hardware encoding, the input-output registers, the operands, and the assembly string. Let's see how we can define the register. We first define a register class, TMS320C64X that is a subclass of the standard register class. We specify the hardware encoding, and we define instances of this class, which are the actual registers. So this is pretty simple. Let's see how we will define instructions. We first have to define all operands, then instruction classes, multi-classes, and finally we will define the instructions. How do we define an operand? We always make a subclass we always make an instance of this class, the operand class. And we have to define a decoder method, an encoder method, and the print method. What these methods do is the decoder takes the hardware and the hardware encoded bits and converts it to an internal LLVM representation. The print method takes this internal LLVM representation and converts it to a string. The encoder is the inverse of the decoder. Now let's see how we define instruction classes. We make subclasses from the instruction class, and we first made the superclass common for all instructions. We define the condition, if the register is 0 or not, the side, if the instruction is executed in parallel with the rest of the instructions. We must define the output operands, the input operands over here. All these are considered operands because there's no other way to describe them as inputs to the decoder. And we specify at which bits every operand can be found, the size of the instruction, and these are some standard stuff. Then we define some subclasses for every type of instruction. For example, for instructions, the first type of instructions at the functional units have this format. They have two source operands, one destination operand, and the value of the operation. The source operands are stored at these fields. The destination operand is stored over there. The operation is stored at these bits, and this is a constant. This is another example. It has also the crosspath. It's for some instructions that use the crosspath, like add and end. Instruction multiclasses are actually like something like templates. You define an instruction multiclass when you have two or more instructions that are similar. In this example, you have two instructions that are similar, but their own difference is that this one has a general purpose register as the first source operand, and this has a 5-bit unsigned constant. And finally, we define instructions. As you can see over here, this is the instruction selection pattern, which is empty because we can't assemble. We have the string, the operands. This is the operation, and this defines this instruction. So we must take the dataset and implement this thing for all instructions for all functional units. So we've done this. Are we done? Not even close. We need to implement all the code for encoding, decoding, printing operands. We need to implement instruction mappings. We need to add a lot of supporting code. And we need at least the Python bindings. Okay. We start working on this, and after some hours, not some hours, some days, I found some problems. First problem was that the converter was not the standard LLVM one, but a different version that produces C code instead of C++. LLVM is written in C++, Capstone is written in C. So I had to convert the converter. Decoding of all fields must be done manually. We have the documentation, we can do it. Instructions with PC relative addressing must be handled specially. It's pretty difficult. You must keep always the program counter, make the calculations correctly. While I was coding support for this architecture, I found several bugs at other architectures that didn't implement PC relative addressing correctly. Another problem are the branches. Branches must be handled with care because they're not relative to the current instruction, but they're relative to the first instruction in the fetch packet. So you must get the program counter, find the fetch packet, find the first instruction of the fetch packet, and then calculate the target address. Another problem is the parallel bit. As you saw before in the assembly, we put 2 bars to show that this instruction will be executed in parallel with the previous one. But this is not encoded in the current instruction, but it's encoded at the previous instruction. So it's pretty difficult due to the way Capstone and LLVM works. It had to be done using some post-processing. After completing all this, we had a disassembler we could use. So what can we do now? You can disassemble everything, but we have no symbols. And we have thousands of lines of this strange assembly code that you can't even calculate when it jumps to another location, where it will return. It's awful. Okay, so let's check the simulator firmware. We use exactly the same tools to extract the internal binary, and this time it's a DLL. So we've got symbols. What can we do? We correlate string references in both firmwares. The same strings should be referenced by the same functions. This is pretty easy to complete. Then we check out branches. Same functions should branch to the same functions. The rest will be fixed by hand, and we can read the code and profit. So, can we actually profit? We said that these products are methodically tested, the best security practices are used during design, so bugs should not exist, right? So, at least simple, easy to identify bugs should be eliminated. Let's see an example. This is a function that is used to extract the MBK and databases in general. The MBK cannot be extracted according to the documentation. This is a security check. First two bold instructions load the address of this string, vmbk1, to register A5. 1 is subtracted, it's loaded to A4. B4 holds, it's a pointer to the database, the string, that's the name of the database that we're going to load. And all this is a part of a memcompare, not the full memcompare. So what this does, it checks if the string starts with vmbk1, mbk, or session obs. These are some sensitive databases that you can't extract. If the test pass, the common open function is used to open the database. After reversing this function, I found that the first argument of this function is the name of the database, for example, cxikey.db, which can be prefixed with the location. This database, cxikey.db, exists inside the flash, so we can use flash /cxikey.db to extract this database. So, what if we extract flash /vmbk1.db? Sometimes one facepalm is not enough. You can extract it at any time. What about other bugs? Okay, all the code has the same quality, and I'm absolutely sure that there are more logical errors. I'm 100% sure. And I haven't searched for buffer overflows yet. I have some strong evidence that buffer overflows exist. Something that's very interesting is the disclosure timeline. I first tried to contact Utimaco the 10th of March 2016. I just wanted their PGP keys or a certificate because I couldn't find them anywhere at their website. After 2 months, I finally got the PGP keys. It's 2 months. Next day, I sent them the details, and after 1 month, I received the first official answer. And after 4 months, I got access to a network HSM with the updated firmware. So I first tried to contact them at March, and they fixed it at October. And the final step over here, so there should be. And you can start cloning. So, any questions? Okay, do you need the mic, maybe?
I'm only curious, how did you debug this stuff?
How?
Did you debug this stuff?
So I have access to the Mac HSM, and I didn't debug this. I mean, I just read the code and started trying all this stuff at the regular HSM.
Because for me, from my point of view, it seems a very nasty architecture. I mean, the parallel unit, for what? I mean, for return to call a function, like how many instructions? 6, 7, I counted, or something like that. And I'm still thinking about how they are able to debug or whatever.
So that is why no tools exist. Let me find this slide. That's why no tools exist. This is the jump, as you said. You have code that's like this, and this is a simple jump. If you try to check out a recursive loop or something like this, no way you can find out what's going on inside.
Yeah,
so everything
exactly. And why? That is my question. Why they did all this kind of stuff for only a jump?
Ask Texas Instruments, don't ask me.
Okay, thanks. Very cool presentation.
Yeah, I can comment on this question actually. The thing is that it's a DSP, it's digital signal processor. It's supposed to work like that. Its main purpose is not to execute code like functional code, it's just to process data. So it's optimized for loops, for processing arrays of data, and that's why it has long delay slots and stuff like that. It's optimized for processing big arrays of data. That's why it's like that. Yeah, and now my real question. Yeah, I'm just wondering, when you saw this picture in IDA, why you didn't email Hexarray support? Because otherwise it would have been boring talk.
Well, why not implement it Capstone, which is open source?
Okay, so you wanted to have some fun.
Yeah, maybe this is why I did it. I don't know. I mean, Capstone seemed nice.
Okay, thank you.
Hi, thank you very much. That was great. The SP320 very often comes with two cores, one being the DSP itself, and the other one can be an ARM, like in DaVinci series. Did you notice some kind of other update that suggests that a side, more application-centric processor could be on the same die?
As far as I know, this HSM comes only with this DSP. Just this. Doesn't have an ARM core or anything else. Anyone else? Oh, okay.
Hi, just a quick question. Did you manage to find did you run some plugin that could allow you to find presence of keys or to notice how keys are stored inside the HSM? Because that's the things that should be protected. Did they use some?
Okay, can we discuss this afterwards?
Yeah, very happily. Thank you.
So, no more questions? Okay, thank you.